trabaja con memorias cuánticas y redes cuánticas, ¿no? Y desde el 2013 es miembro de la Facultad del Departamento de Física de la Universidad de Calgary, ¿no? Es un investigador principal del laboratorio Cloud Lab, ¿no? Y ahora también hace investigación relacionada con enlaces satelitales cuánticos, ¿no? Y también tiene una compañía, un spin-off, ¿no? De tecnologías cuánticas, ¿no? Que se llama Quantized Technologies, ¿no? Y la idea es que con esa compañía puede proveer de encriptación cuántica segura, ¿no? Y también desarrollar componentes para el uso de tecnologías cuánticas.
Muchas gracias. Y gracias a los profesores de la División de Información Cuántica por invitarme a este congreso. Y es un honor para mí de darle esta charla sobre nuestra investigación en redes cuánticas en Canadá, en Calgary. Me gustaría poder hablar en español, pero lo siento, mi español aún no es suficientemente bueno, por eso desafortunadamente continuaré en inglés. So, very sorry about that, but it's going to be painful if I speak in English for everyone, for in Spanish. But maybe in a few years I'll be back in Spanish. So, questions afterwards. I know they will have question time as well. If you want to ask a question in Spanish, maybe I'll understand it, or maybe there'll be people to also translate, so don't hesitate as well. Okay, so my research in my lab is about quantum networks, and I thought that for this, when people give me 50 minutes to talk, I'm going to explain a lot, and so I want to try to explain what they are, what is a quantum network, why do we want quantum networks in the first place, and then most of the talk is going to be about how do we build them, because I'm an experimental physicist, and so I like to build things, and I like to talk about all the things we build and how we do it. So, a lot of it's going to be on that. So let's see if I figure this out. No? Okay. So I'm just going to take this opportunity to just introduce, maybe some of you haven't heard of the University of Calgary. Calgary is a city near the mountains in Canada. There'll be some beautiful photos and you'll see how beautiful it is. The university has 5 campuses. It's about 50 years old, and there's about 30,000+ students in Calgary. We do a lot of quantum research in Calgary. We've had a center called the Institute for Quantum Science and Technology, which is about 20 years old. So for 20 years, we've been doing research in quantum information and quantum technology, and we're expanding right now with lots of new people coming. We're doubling the number of people that will be researchers in the field over the next couple of years. We are also supporting the quantum ecosystem, because quantum technology is these days not just university research, it's also companies, it's products. And so a new initiative is called the Quantum City, which will include a new clean room building, and we have lots of activities going on, from business conferences to challenges to hackathons and an accelerator program for startups that come in quantum technology. So I have the websites down here if somebody wants to look up, but that's the idea of what quantum technology is becoming these days, when it becomes real products and real things that people use. Yesterday I was talking to people, and I realized that not too many are aware of this nice opportunity for exchange with specifically to or from Canada. So if you have students in Canada that some of the profs would like to invite, Or vice versa, if you are interested in going, there is this good exchange program called MyTax, which gives a $6,000 scholarship to just travel and visit for a couple of months. About 12 weeks, I think, is the minimum. So I encourage you, if you're interested in, exploring things or getting some skills or exploring what people do other places, this is a really nice program. So look into that. So MyTax Global Link Research Internship. Okay, so now on to my work. So here's one of those beautiful pictures. I promise this is me taking it. This is one of my friends here walking, and this is a glacier. So that's all about 2 hours drive from my home. The lab that I have is called the Quantum Cloud Lab. Here is how many we are last year. So this is a bridge that's in one of the buildings, and we're becoming a little bit of structural engineers. We're checking how many people can be put on the bridge before it drops down. And so far so good. So we'll keep expanding until it's no longer safe. Good funding, so I always acknowledge the funding agencies that we have that support our work. And if you want to look up some of our details here, we have some both social media presence as well, so you can find us there and see what we're doing. So in this talk, we're going to start with defining what is a quantum network. Because if we don't know what we're talking about, then it can be hard to understand why we're doing it and how we should do it. So a quantum network, at least the way I see it, is a system that facilitates distribution of quantum resources over a distance. Right? So it's a little bit broad, deliberately. So we have to have some sort of system, a device that you can use to share quantum resources. To give some examples, it could be some optical components, channels, sources, detectors that transmit quantum states encoded into photons. You can in principle also do that with cryogenically cooled wires. You could send electromagnetic quantum information over wires as long as they're cold enough. You could also have like a quantum shipping network where people put quantum devices with a defined quantum state in a box, and then they pay UPS to send it to somewhere, and you take it out of the box, and well, that's a quantum network because you sent a quantum state from one end to the other. And then we can generalize it. Any of those methods you could also use where you have two systems that are entangled, and you keep one of them and you send the other one. Now you have an entangled state that is over a long distance, and that becomes a resource as well. You can use that now for quantum communication at some point. So any of those things could be an example of a system that facilitates the distribution of quantum resources. And the obvious choice, though, even though there are many options, is going to be light. Photons are good because, well, they're really fast, which is good, so you don't have to wait for a long time. They are kind of easy to isolate, right? So we receive photons all the way from distant galaxies from the beginning of the universe. We're not receiving electrons from the universe, so clearly photons don't interact too much. They're easy to send over long distances, so that's a good thing because you want to maintain the quantum system. And then you also actually have a lot of quantum degrees of freedom. So you can encode the quantum information, because if you want to send some information, well, you have to have some way of encoding it. Specifically, of course, we know that when we are working with quantum information, we often talk about quantum bits. So we have to find some way of encoding a 0 or a 1. And a popular one is to use polarization. So we have horizontal and vertical polarization. They're orthogonal, so one could be a 0 and one could be a 1. And we can also create superpositions, and we can compare and measure different bases, and we have devices that do that. Now, there's lots of degrees of freedom. You have spatial degrees of freedom of light, different paths, you can have different frequencies, you can have different orbital angular momenta. One other degree of freedom that I will highlight, just because we use it a lot, is also the temporal degree of freedom. So we often encode quantum information into what we call time bins. So here's a picture of what that looks like. Basically, you can have a photon being either sent early or late, and you can create superpositions of those by creating an early and late superposition. For example, you can send one photon through an interferometer that has a different path length. It gets split in two at the input of the interferometer, and then when they meet again, you have two options, and since you don't know which path the photon takes, it becomes a superposition. And the phase between the superpositions then depends on the path length of that interferometer, so you just have to control that very stably. So that is a very nice degree of freedom that we use, because when you send it over a long distance, it doesn't change. The distance, the separation between two pulses, when you send it, will not change over time. Polarization and other degrees of freedom, for example, spatial separation, will tend to be disturbed, so they're not that good for long-distance computation. So we focus a lot on this particular encoding using time bins. Okay, so now the question is, well, how would you send the light exactly? And that depends a little bit on one of the key factors that I'll touch upon, which is the distance. Because even though photons do travel very well, they do get lost on the way, so you will have some loss of photons. And of course, if your photon is lost, well, then you can't see it anymore, or it's not going to arrive, and your quantum network is broken. So when you consider loss, well, there's two main ways of sending light from one place to the other. One way is just to send it through free space, so you have a laser beam shooting through free space. And figuring out the loss is a bit complicated because, well, you have air and turbulence, and if you send along the Earth's surface, eventually you also hit the curvature of the Earth, so you actually can't send it that far. So this is actually often mostly used when you're communicating with something that's not on the ground, so in space with satellites. Another common way of sending light that we all use for our classical communication is to use optical fibers. And in optical fibers, there is this problem that there is always going to be some loss. It is down to about 4.2 decibel dB per kilometer, which is pretty low, which actually means if you have a 1 kilometer long fiber, only about 1% of the light gets lost. About 99% get through, which is impressive, because think about it, that's a mirror. It's like having a glass window that's a kilometer thick, and you get that much light through. But since it's exponential, the loss, it does mean that you hit a limit as to how far you can send the light. So it really depends on where you want to go, where you want to connect to, if you want to build your quantum network and share your quantum information. Okay, so before I elaborate on those, because that obviously is going to then determine how we build our quantum networks, I just want to have a little point here on why we want quantum networks. This is going to be my shortest section because I want to get to the experimental details. So, use cases for quantum networks. One is quantum key distribution. So I saw some posters the other day on quantum key distribution. So for those, it will be very, very obvious. But you know, quantum mechanics has ways that you can utilize quantum mechanics to send information, to establish a key for encryption. So a random string of zeros and ones that two users can share over a long distance. And they can verify that nobody has intercepted that key by using the laws of quantum mechanics. So those are called quantum key distribution systems, and they're actually available to purchase right now in some versions as well. So that's one reason, secure communication. You can also think about distributing quantum computers. So either because quantum computers are so expensive and big that you can't have them all in one place, and you may want to connect them together if you want to do more complicated calculations, and you need a network to connect them. Or there's also some cases where you can combine sort of the idea of quantum security with quantum computers, and you can do calculations on a quantum computer without the quantum computer knowing what computation it's doing. That's called blind quantum computing. And so it's a fascinating idea that you can keep your information that that's confidential to you, even if you're asking the computer to do a computation for you. And then there's also applications to quantum metrology. So there's some papers that show how you can enhance the sensitivity, for example, of optical telescopes for astronomy by using entangled pair sources. So the photons that come from the faraway object that you're observing will be interfered with an entangled photon source, and then you can get an increased resolution on that image. That's probably the most distant application of quantum networks, just because you need a very high rate of exchange of photons in particular. Okay, so that was the first two topics of the talk. So now we're on to the third and longest one. And of course, there's going to have to subdivide that a little bit too. So as I said, the first thing we have to figure out is just, how do we construct the quantum networks based on this real fundamental loss scaling that comes from the fact that you have to send it over a long distance. And then I'm going to talk about some of the critical components also involved. And I'm going to focus on the thing that we do a lot in my group, which is to work on light matter interfaces. So getting that light that's traveling really fast, which is great when you want to share it, but bad when you want to store it for a little while. So we also have to realize quantum networks. We actually have to build quantum networks, and we have to have an interface at the quantum level between light and matters. And to go easy, we'll start with a short distance here. And when we're talking about short distances, what we really mean is something on the order of less than 100 kilometers. So if you're sending, let's say we're using optical fibers because then we don't have to worry about turbulence or anything in the air, then we can look at what is the loss when we travel over 100 kilometers. So you just insert the loss formula here with 100 kilometers, you see that you get about 1% of the photons. That's not too bad. You can still do some decent communication that way. So we can just send the light straight through the optical fibers. We don't need to do anything else more fancy, just sending the photons into a fiber and detecting them, and we can use and develop some of the protocols. So that means that if, for example, you want to go to these mines, which are the Nika mines, which are about 150 kilometers from here, it's pushing it a little bit, with the 100-kilometer limit. But if you want to go downtown here to the Historical Museum of the Mexican Revolution, so that's just 16 kilometers, you can set up, your friend can go there, and you can build a quantum network to those places, and you should be okay. So, because it's fairly straightforward, this has been done already a long time ago, just using optical fibers. So quantum networks or quantum links have existed back from more than 20 years ago. For example, QKD was implemented in Switzerland to secure an election, at least just for a test, for a trial, about more than 20 years ago. People have done teleportation. This is an experiment that we did about 10 years ago in the city of Calgary, where we did teleportation. I'm not going to explain what teleportation is, just be sure that it's not the science fiction version of it. It's a little bit more sciencey than that. And people have distributed entangled states or fibers, even that go under the water. Here's an experiment example from in Italy, between Sicily and Italy and Malta, which is an undersea cable that people exchange entanglement over a long distance. I think it's 80 kilometers or something, 96 kilometers. So, these things have all been demonstrated. What we're working on in the lab is we're working on quantum cryptography, as I said, and we're working on a specific version of it that's called measurement device independent quantum key distribution. And I'm not going to, again, talk too much about that. Just point out that for those who know quantum key distribution a little bit already, that this particular protocol has some advantages in terms of not relying on the security of the detectors. And one puts the detectors at a central node, and we have the two users who want to exchange the key, both sending light to this central node. And that makes it more cost effective because all the detectors can be in one place, and these detectors tend to be the expensive part. I have a picture of them. Yeah, so these are the detectors we use for our experiments. They're superconducting nanowire single photon detectors. It's a very long word to say. And the main problem with them is that you have to cool them down to just below Kelvin for them to be superconducting and to work. But then they are very, very good. And what we do in our experiments, just to reintroduce the time bins, is that we look for certain detection patterns on the detectors at this output, and that establishes a form of correlation. So we can tell from those measurements that Alice and Bob, the two users of the quantum network, sent, say, opposite quantum states or quantum bits values, but the measurement device in the middle doesn't know who sent what. So that they don't get information about the actual key. And that's sort of the trick behind why this is secure. And even your adversary or enemy can take over this station, and they cannot break your hack your system. So we're developing, this is the topic of our spin-off company called Quantized Technologies Incorporated, and we're building a system that we can presumably sell to customers who want extra security. So you can look up more about what we do there if you want to. So now I'm going to jump a little bit over to the long distance, because I said this short distance is at the level where companies are building systems and producing it. So it's not really research anymore, it's more technology. For the long distance scenario, the solution is also somewhat simple, and in fact, there are two solutions. But let's just look at what we mean by long. So by long, I could mean something that's, let's say, over 2,000 kilometers. That's really long. It's much longer than 100 kilometers. And when I look at the transmission of light, I get something that is 10 to the minus 40. So that is a very, very low probability of getting a photon, so long that it's not worth waiting for. So we have to figure out something else. This, just sending the light and using an optical fiber for a quantum network doesn't. And there's maybe two approaches, general approaches. One would be, I think the point would be, where can you go if you wanted to go such a long distance? I could recommend you going to this spa here in Japan. It's about 11,000 kilometers, so that's a really long distance. In this spa, you can bathe in wine, so it's a really interesting experience. You could also maybe go to the Gnome Sanctuary in the UK. It's about 9,000 kilometers. So if your friend goes there and you want to have a quantum network, you definitely need another method. So one way of establishing a quantum network over an even longer distance, the first option, is sort of a cheating way, because you just make a network that consists of short links, and then you merge them together. But at each of the nodes of this link, each of the interface between the different channels, everything, all the quantum information gets converted into classical bit values. And so if your enemy takes over that station, they get access to all the information that you have. So for that reason, these kinds of networks are called trusted node networks. You have to trust the node. You can maybe put your military there or something like that, but you do have to trust it, and that limits, how good it is if you want it to be secure. It also doesn't involve the exchange of entangled states, so that's not possible. So if you require entanglement for whatever protocol you want to do over your network, it's also not going to work. But it is a good way to get your network started and then upgrading later on. So this is the approach that was spearheaded by China. So they started with a 2,000-kilometer link between Shanghai and Beijing, which back in 2017, And they have now expanded that to many, many cities. So they actually have a full-fledged sort of quantum network based on trusted nodes, and I guess they have their army guarding all the nodes so that they're secure. And other countries are following the same way. I mean, I just give some examples of the UK. They also have a plan for what they call a backbone quantum network. But let's say this is very limited in how much you can do with it. Another idea is to say, well, let's not go through optical fibers then. Let's skip the optical fibers and find another way. I said that the free space transmission of photons is a little bit more complicated because you don't have this automatic loss due to the absorption or in the fibers. So what do you have? Well, that depends what your light travels through. And if you can skip the atmosphere and go into space, well, then there's not really anything that obstructs the light. It will travel for an infinite distance. But, as we all know from some of our basic optics, there is some loss coming from the fact that the light beam that you're sending will expand over distance. So that's what this sort of kid's illustration here is my attempt. So let's say you start with some light and you have the light, the area of the light expands as the distance grows, and you have some receiver detector that has some finite area, right? You cannot just have an infinitely large detector. So you have some way of collecting the light. Then the amount of light you collect is going to drop as the distance increases, and it's going to drop with just the ratio of this area to the area of the beam, and this area of the beam is going to grow with the square of the distance, right? It's just the area of the circle. So if you look at the sort of formula, initially maybe the detector is smaller than the beam, larger than the beam, and then it gets smaller, and then it starts to only detect part of the light, not all of it. So you get some scaling that looks like this, and you can compare the fiber optic transmission to the transmission in vacuum, and you can see that initially it's over some distances it's less efficient, but at long distances it becomes really significantly more efficient. And notice this is a logarithmic scale here, so you know this gap is huge in actual values, like it's at 3 to 4 orders of magnitude. So that means that, well, maybe you should go into space. And lo and behold, that was also spearheaded by the Chinese. They sent up a quantum satellite in 2017-16 as well, and they had a lot of publicity and very impressive experiments done with that. And since they set it up, a lot of other countries have followed suit and want to do the same. In Canada, we actually had a quantum satellite planned for a satellite for even longer than in China, but the funding wasn't as good as theirs, so they could launch it much earlier than we could. So following that idea, we've also set up a satellite ground station. We would like to do, you know, all parts of this network. In Calgary, here's a dome, and here's actually a picture of the ground station. There's the laser here, that's the beacon laser, so it helps the satellite find the ground station by looking for a spot on the ground. And the green light here is actually the satellite's beacon laser that we use to center so we can align ourselves exactly. So it's like aligning it to a star that's just moving really fast. And then the quantum light, so that we use to send the quantum information, is at a different wavelength, so we can filter all the other classical beacon lasers out. And so if you're into Star Wars mythology, apparently according to this, we're bad guys. So maybe we'll work on our attitudes. Here's how it works. So as a drawing here. So here's a ground station. Here's a satellite. This is a low Earth orbit satellite, so it's about 500 kilometers above the ground. As it flies above, we intercept its beacon laser and send our beacon laser. We do a little bit of alignment, and then over this duration of the pass here, we're collecting the signal from the satellite. And we actually moved our ground station one time, and put it in a new space. As you can see here, now the ground station is together with friends, other telescopes at the observatory that we have down just south of the city of Calgary. And now we're doing experiments there. Here is an example of what the data looks like. So here you see the single photon counts on avalanche photodiodes in the 4 different bases that are used for quantum key distribution. But as you can see, sort of for those who don't know quantum key distribution necessarily completely, you can see how when we get at some point where the satellite is closest, we have the most counts and then it drops off. Then we can analyze, this is specifically used for quantum key distribution, we can analyze how much key we get. You know, we get about 650 kilobytes of, so 650,000 detections that we can use from the satellite, and out of that we extract about 167 kilobytes of actual secure key through some steps that we have to correct for errors and whatnot. And here's a Canadian quantum satellite ground station that we want to connect with. Right now we're connecting with the 2 Chinese satellites. Somehow we managed to get away with that. The quantum satellite that Canada is launching, well, they said, I think in 2025, that it's now as a launch date. That's not led by us, that's led by another university, but we are serving as one of the ground stations for the network that they want to do. Okay, medium distance. Here's where it gets interesting. So, in the medium distance, we say somewhere between 200 and 2,000 kilometers. Let's say we pick something like 500 kilometers here, you still have a very, very low probability of light coming through. But it may not be worth doing a quantum satellite because, well, the weather is bad, the quantum satellite doesn't work, and they're not overhead all the time, so you have to wait. So it would be nice if there was another solution as well for this medium distance. And the solution will help you then to, for example, communicate with your friends who is visiting the Smiling Peanut Jimmy Carter commemoration, which is in Plains, Georgia. Or if you happen to be visiting, or your friend is visiting the Museum of Bad Art in Boston, those are the kinds of places you can connect with such a quantum network at intermediate distances. So, the solution is called quantum repeaters. And here where it gets nicely technical, but also really, really interesting. So, why is it called a repeater? Well, your aim is to repeat the information. And this is the name that's used for classical communication. So anytime a fiber optic link connects users that are a couple of 100 kilometers apart, there's a little amplifier that amplifies the signal so that it's, even though it gets attenuated and lost, it gets boosted along the way. Now, in quantum mechanics, we cannot amplify quantum signals. That's called a fundamental theorem called the no-cloning theorem. So we cannot copy quantum states. So that's not going to work for quantum states. We have to find another solution. And the solution is called quantum repeater, and it works by distributing entanglement. And it works by, instead of distributing entanglement over a large distance, you split the long link into many smaller links, and you verify, we call it herald, but we say like you get a notification when entanglement has been generated over the small link, which is short enough that the probability is not too low. And then you can connect all the links together when two neighboring links have confirmed entanglement over the shorter distance, then you combine them by another step. So it's sort of a stepwise protocol. I'll try to go through this just a little bit like a tutorial style so we'll get something out of it. So medium distance quantum repeaters. It's based on entangled sources. So here's where we start out over what we call one elementary link of the quantum repeater. So let's say we have 2 sources of entangled photons, 2 red hexagons, I guess. They are signifying sources of entangled photons. The yellow dots, they're the entangled photons, and they have some labels here, A and lowercase and uppercase A and lowercase and uppercase B. And so they're created in some state, an entangled state here. They will come later as what they are. So this signifies an entangled state. And so the entire system is this combined entangled state of the 4 particles. We then send one of these photons into a quantum memory, and we send the other ones over the long distance where they interfere in a beam splitter, and they give us a projection onto one of these entangled states. These are called the Bell states. So as you can see, these are now, just as an example, horizontal and vertical polarization entangled states, and we have two types, the psi states and the phi states here. So the psi states are anti-correlated and the phi states are correlated. How does this measurement projection relate to this input state? Because this is a measurement of the two photons, lowercase a and lowercase b, but this state is expressed in terms of the product of the A photons and the B photons. Well, the trick is to expand this expression into 4 terms. So you get something that looks like that. Now we've expanded it so that all the lowercase and all the uppercase photon are grouped together. And then if we measure the two, let's say one of these psi states here, then the underlying ones here. So let's say we measure the photons that were transmitted, so the lowercase ones to be psi plus or psi minus. Then we also now know that the 2 remaining photons that are in the quantum memory are all in the specific entangled state. So now what this measurement does is that the measurement gives you a signal that we have entanglement in the quantum memories, and that entanglement exists over a long distance. Of course, sometimes these photons that are traveling will be lost, but then we don't get the signal that it's okay. We only get it when the 2 photons made it and they were measured in that particular quantum state. So that allows us now to synchronize the entanglement generation over subsequent steps. So what I said about quantum repeaters, you can have a distance A and B that's too long to span with a single link, but you can split it into 2 elementary links, which are just like the ones I've described before. So over the first elementary link, we do the process of creating entanglement between the quantum memories, and then at some point, maybe a later time, we get the entanglement between the neighboring link. And when we do that, then we emit the photons from the quantum memory, and now we've combined the entanglement over the longer distance. So the quantum memory is essential because it allows this process of merging the neighboring link to become non-probabilistic anymore. It becomes deterministic as long as efficiencies are high. So we can look sort of at here is sort of how to express the rate of entanglement distribution in a quantum network. I won't go into the details of it, but just point to some graphs here where what's listed here is sort of the probability for every trial. So you define a number of times that you want to attempt for all of the links to establish entanglement until you say my quantum memory is probably not working anymore, and then you give up. So that's this M number here, and then this is the number of elementary links, being 2. And when at a short distance, you can see that, well, you want to minimize the number of trials. You actually don't want to have to try many times. But then over a longer distance, because the losses increase and the distance of these individual links increase, then you have to try more times, and it becomes an advantage in terms of the probability the more time you try. And a similar thing, you can look at how many links you need, and the longer the distance, the more links will give you the higher rate. Whereas at a short distance, there's some losses with finite memory efficiency that mean that it's better not to use the quantum repeater. So this is how we build a quantum. This is sort of the concept of the quantum repeater. Let me skip this because we are going sort of like shorter time. It's just advocating for what's called multiplexing, where instead of sending one photon over the long link and then waiting for the signal to come back before sending the other one, it's best if you can keep sending photons even into the memory and over your link with as fast as rate as you can. But for that, the memory that you're using has to have a multi-mode capacity. It has to be able to store many photons at the same time, and not all quantum memories can do that. So that was the basis behind that. So quantum repeaters and elementary links have recently, a year or two ago, been demonstrated using exactly the same platform for quantum memories that we're using. In 2 experiments, one in Spain and one in China. So this is a very promising way of building the quantum repeaters by using the quantum memories that we are working on. So let's get to the light matter interfaces. And I'm not sure. Let's check my time here. 15 minutes. Something like that. Okay. Thanks. So this is a big part of the research we do in the lab, and I like atomic physics. So this is the part that also I find really, really interesting. But whenever you work with light, you go from working with light and you work with atoms, life becomes really, really complicated, because atoms are really complicated things. The atoms that we're working with are called the rare earth atoms. So in the periodic table, they're down almost at the bottom. The reason we work with them is that when you look at their electron structure, the valence electrons are the ones that are in the 4f shell. But when you look at the spatial distribution of the electrons, they're not actually the outermost electrons. And that means that even though you put this atom, these rare earths, into a crystal, the electrons that are interacting with the light are somewhat shielded from the crystal environment. And that means that you can sort of buffer the quantum information. You can be a little bit protected that way. And so this is a really unique property that all the rare earths have. So, as I said, we put them into a crystal, some kind of host material as a dopant, and because the crystal is not completely regular, the different transitions for different ions, or because they're ionized when you put them into the crystal, they will be slightly different. So you have this inhomogeneous broadening of the transition lines of different atoms, just because they're located in different places within the ion. So we have still a nice, narrow, homogeneous line, which means that the quantum state is nicely protected, but it's spread over a large area. And that actually becomes very, very useful for the kinds of memory protocols that we're doing. And so they also have many different wavelengths, and we can have very long times of storing the quantum information, which is measured by coherence time. So the only problem is we need to use cryogenics. It doesn't work at room temperature, but then we have the Canadian advantage that, we're almost at cryogenic temperatures a lot of the time, right? Not a very good sales pitch, but, it does get cold. So how do we use these kinds of materials to make a quantum memory? So there's a couple of different methods. I'll show one of them here, and they're classified as photon echo types of memories. And what we do is, well, let's say here we have our, transition that we're working at the ground state, and we have an excited state. All the atoms will be in the ground state level. And then a photon comes in, it gets absorbed by all of these atoms here. So, since we have a single photon, we don't actually know which atom absorbs the photon. So the way you express that is that you go from the input where one photon and all the atoms in the ground state gets transferred into 0 photons, and then a superposition of all the possible atoms that could have absorbed that photon. So it's we call it collective excitation. We don't know which atom it is, but one of them does. They absorb a photon, and because they have, it's small maybe down in the back here, because they all have different transition frequencies, each depending on which atom absorbed the photon, we will have a phase that evolves with time. And that means that this state that you created dephases. And the aim is to control the rephasing some way so that you get all the atoms back back to the state where this phase is 0, because then you reproduce the state. You can think of it a little bit as time reversal. You get back to the state that you had when you absorbed the photon, and then what happens is that actually the photon is emitted. That's why it's called an echo, sort of like an echo of the input photon. The way that we realize this controlled rephasing is in a way that's actually not sort of like almost cheating a little bit, but it works very well. So we take the atoms and then we remove some of the atoms from the ground state here. So now you see we have some of the atoms have been removed over to some other level that we call the, I think here the spin level or the auxiliary level. So there's this additional level that we do optical pumping to transfer the atoms. We also call this spectral tailoring because we're tailoring the absorption spectrum, and all we need is for this transition here to have a longer, sufficiently long lifetime. Okay, so we have these peaks now here that are spaced by some frequency capital delta, and there is some lowercase delta in width. And if you look then at the phase here, and it gets a little bit smaller, so I'm sorry that it's not a little bit bigger, you will see that I've replaced now the phase with an integer multiple of this fixed phase delta here. So we just have integer numbers of possibilities. And at the time, and so the phase here for each of the atoms is just going to evolve like this. There's going to be some integer multiples of 2 pi n times delta times t. And at a time where you have the time equals to 1 over delta, so delta is a frequency, so 1 over delta is a time. At that time exactly, all the phases become some integer multiple of 2 pi. And any integer multiple of 2 pi is just 0 as a phase. So it's the same as a phase being 0 for all the terms. And so we can reproduce the echo, and get the echo, a re-emission after exactly that time 1 over delta. And so this thing, because we have like a series of peaks in the absorption spectrum of the atoms that we created, it's called an atomic frequency cone, or an AFC quantum memory. Okay, I will go through these. So now we have a choice, which rare earth ion do we pick? So we have a couple of different ones that we could look at. So we looked at helium into lithium niobate. So both the host and the ion matters. And when it comes to those, we actually have them in waveguides. So you can see the light guided through the waveguide here. And we have an absorption line at 794 nanometers. And we have, again, back to the atomic frequency cone quantum memory, we have here an experimental example of such a frequency cone. And you see here that, you can see the axis here, it spans over a total of 8, that's actually 8, but that's like 12 gigahertz. So it's a really large range of frequencies that we can store that we can use for storing the light in. And that becomes very important because if you know the width of the quantum memory in the spectral domain translates inversely into the width of the pulse that you can store. So the shorter pulse you can store, the more of them you can send, and the faster the quantum communication can be. So high bandwidth, as we call it, in the spectral domain becomes really important. Here's an example of such an echo here. And this was the first time that solid-state material was used to store entangled photons back again. This is also close to 10 years ago from the greenhouse part experiment. And lots of follow-up work also done on that. Now, the problem with it is that the efficiency is not very high, and here the scale is on nanoseconds. So in order to improve that, we have to choose a different material that doesn't have this gap here where the absorption is sort of a background absorption that's not contributing to the quantum memory. And we can use a different crystal, and we can put it inside a cavity that enhances the interaction between the light and the atoms. And so here's an example with another crystal that has helium, but here it's helium, yttrium, aluminium, garnet. And here's the crystal where we polished, we coated the surfaces so they're reflective, and we just couple into it inside the cryostat. And then here's an example of the frequency comb. You can see that it has much less background, so that's better. And we have an efficiency here of about 30%, a little bit below 30% for this one. So better than the about 1% we had in the previous one. And we store in tangled states, and for showing entangled storage, you have to store, qubit states, and we show that the qubit states, the input and the output is the same. We also use fibers, so fibers often come with erbiums with different rare earths in them. And the good thing is that it's easy to connect those and store and use them for quantum memory, so we've done a lot of work in that. And since I'm really running out of time here, I think I will see if I can go to some highlights of another crystal here that we're using. This is terbium, so we've gone through erbium, terbium, thulium, and they all have different properties. Here we have some good microwave transitions, so we can also work with microwave fields. And the last thing I want to show here that's less on the technical side is another type of quantum memory protocol. I'm not going to explain it, but what it does that's really nice is that we're able to, with this quantum memory protocol, to store many photons at the same time in different spectral regions of the absorption line, and then we can recall them on demand when we want to. And here the results show like different spectral bins and different control pulses, and then how you recall the light at different times. And so this allows the concept of multiplexing for the quantum networks and for the quantum repeaters that we want to build. Okay, so other things we do, these are the final 2 slides. We do some work on error correction in, for the quantum key distribution. We're working with a new material of molecular molecules that contain a rare earth and then crystallize. And we also work with detection, we're good at very good photon detection from biological systems. So we're delving into the realm of quantum biology together with theorists. We are working, as I said, in terbium also with the microwave regime. We're working on creating some more exotic entangled states of more than 2 photons. And then we started recently also trying to build everything that we've done so far, but on integrated photonics, because that's going to make it compact. And here's the last picture, more nice nature pictures from Calgary. So sorry for the length, but thank you for your attention.
¿Preguntas?
Hi, hello. Thank you for sharing your work with us. My question is there any relationship or application between the quantum networks and the work in the area of electronics and magnetic nanotechnologies?
I think that's the first part.
Thank you. Yeah, the first one is any relationship or application with network, quantum network, sorry? Electronic and magnetic nanotechnologies.
And the magnetic technology. Okay, so I mean, quantum, so yes, because spins are very good qubits, and the quantum networks is about connecting qubits over long distances. Of course, the networks have to use light, because at least for now, that's the only thing that really works. So then the question is, how do you transfer the spin degree of freedom, the spin information of the qubit into light? So you have to create an interface between the optical, the photon qubit, and the spin qubit. And there are ways to do that. Depending, it's very specific to the exact physical system that you're using. For example, in nitrogen vacancy centers, you can have spin states that you can transfer to single photons. And in other interfaces it's harder. The reason, for example, that we're working with microwaves is because a lot of quantum computers use superconducting circuits, and they use microwaves. And microwaves cannot travel in an optical fiber, not even a cable, at room temperature because there's too much noise. So you have to cool it down. You can't have a cryogenic cable between cities. So you have to convert the microwave quantum information into an optical state. And that's, you can do via atoms. They can be used as sort of the transformer between the two energy levels of the two types of information, two types of input. Hope that answers your question, but happy to follow up if you have more.
Hello, I have a question too regarding the use for a qubit in quantum information, like beside the application of in cryptography, there is any other reason to use quantum information beside instead of normal information, like there is more information that we can travel easier, or why do we have to take or what can be done now without using quantum computers?
I think so your question is whether there are other reasons than cryptography to use quantum information, especially over distance, I guess. Because you know quantum computers, of course, that's one reason, right? But then why to use quantum, why to code information in a quantum unit? I think most of the protocols that I'm aware of relate to some form of security, not necessarily cryptography. There are protocols for secret sharing as well, where you can have 5 people, let's say, share an entangled state, and they all have to agree to measure to get the information about what the state is. As I said, there's connections between quantum communication and computing with these protocols like blind quantum computing, where you can avoid a computer knowing what it's doing. You know, maybe you don't want, let's say the example some people have is like, let's say you're a billionaire, and you want to check out what's the, like how's a company doing, and you want to look up a database. But as soon as you're afraid that somebody at the database is checking who's watching and is going to buy the stock there before you do it, right? If you can send in a request that nobody knows about what you're asking the quantum computer to do, then you can hide that information about what you're actually asking to do, and you can keep it secret. So there are use cases where you don't want people to, let's say, know what computation you're doing. Or let's say you're a medical company, you want to simulate some molecule. You also don't want the competitors to figure out what it is. So as far as I can tell, most of the applications for quantum networks relate to some form of privacy or security, but not necessarily cryptography.
I mean, there is like some other advantages in quantum information that you can collect more information in what classical.
Yeah, you can encode more information, but you're always going to be, it's always going to be more difficult, and quantum information will always tend to get lost on the way. Since there's no way to recover that, it always ends up meaning that quantum information is slower. Also, the detectors will be slower. Everything tends to just happen slower. But so you shouldn't aim for it for just the speed. It's always going to be behind the classical technologies. But when you want speed and security, then you can think about maybe I can do better than just using qubits. Maybe I can use higher dimensional systems. You can use tricks to make it more efficient.
Una última pregunta.
Good afternoon. My question is regarding the quantum satellites. How many years is it going to take us to build the quantum satellite arrangement that you mentioned before?
So you're asking about whether what's the status of building them, or how to do it, or what's the next steps?
Just what are the next steps? Is it going to be better than our actual satellites? You said that is the next step in our technology, so how many years is that going to take us to build the infrastructure?
I don't get the full extent of your question. I'm not exactly sure what part of the aspect of the quantum satellites you're asking. Very sorry. I mean, I can say a little bit about what the plans are for quantum satellites in general, what people want to do with them, and what also my opinion maybe, because I think quantum satellites are tricky because, so I thought most of the time in Calgary it looks like it's very nice weather, just like here, almost always sunshine. But when I was started using the quantum satellite, I realized how many times there was like a thin layer of clouds, very high up, and then you kind of use it. So there's so many ways where quantum satellite links get broken that I have a hard time imagining that that's going to solve the quantum networks over long distances, but may help them in some cases. You will have to have a way of distributing signals over the ground to, let's say, a ground station that's not in a clouded area. To realize a quantum network with quantum satellites, you would then have to do the same as they're doing with, let's say, the fiber optic, the networks that, let's say, SpaceX is building with a swarm of satellites, because they have to be connected to each other and send information between each other over long distances. So technologically, it's a huge, huge investment. In China, again, being ahead, they've launched a couple of new satellites that are micro or mini satellites, and their next step is to launch also a geostationary satellite, so that they can connect two different satellites at different ends of the Earth by going up to the geostationary satellite and then back to the other satellite and then down to Earth. The geostationary satellites are like, I think 30,000, 50,000 kilometers away, so it's like a lot more than 500. So it's much, much harder to get working and get the good rate of photon detection. It's going to be very slow. I'm happy to follow up with your questions afterwards. Maybe it's easier to talk to if you have more that you'd like to know.
Thank you very much. On behalf of the next